Okay, I'm really excited to talk to you today about voltaic cells. Voltaic cells are a really cool application of redox chemistry, which is this oxidation and reduction type chemistry where electrons are being passed around and some things are losing them and some things are gaining them. And one of the important applications of that are batteries. And the simplest chemical battery is called a voltaic cell. This is an electrochemical cell in which a spontaneous chemical reaction generates an electric current. And so the process is going to happen spontaneously if you set it up the right way. And then as you're doing that, then you're causing a flow of electrons. That is what an electric current is. So let's talk about what that looks like. We have really what are called half cells, two of these half cells. And we could kind of picture them as at least I do, beakers. So if I have kind of two beaker here set up, here's one, dun dun, and then here's another one right next to it. Then if I fill the beakers with electrolyte kind of solutions, so put some electrolytes in here. So remember that an electrolyte is a solution that has ions in it, which allows for a flow of current. And then if I put a couple pieces of metal in here, here's kind of 1 and 2. Let's call these electrodes. And let's make this electrode zinc. And let's make this electrode copper. It's kind of the common battery setup. Copper, zinc. It kind of depends on what it is, but copper zinc is kind of the go-to for voltaic cells. It's one that's very well studied. So the zinc electrode then is in an electrolyte solution, and when I hook it up with a wire, here's my wire to kind of my setup over here. We're hooking it up to this electrode. So now I've connected my two electrodes, these pieces of metal, with a wire here. Then the zinc is going to start to lose electrons. So my zinc, which is just zinc metal as I would find it on the periodic table, is going to start to produce zinc ions in solution, right? It's going to undergo oxidation, right? So the half reaction that's occurring in this half cell is zinc is going from zinc to zinc 2+. And how many electrons is it losing in order to do that? Well, it needs to lose, in order to balance out my charges here, it needs to lose 2 electrons. Now, where do those electrons go? Well, the electrons go up through the wire. They can travel up through the wire and then get gained. It's terrible English. They're going to be gained by my copper here. And when my copper then gains these electrons, then the copper that's in solution, if we have some copper 2+ in solution, then these extra electrons that are getting gained, I'm keeping it, by this solution then are going to start to plate out onto this electrode. So this electrode then is being consumed. So this zinc electrode is putting ions into solution, and this one is getting plated on. So this one's going to get larger as the copper gains those electrons and plates onto the electrode. So for gaining electrons, that's reduction. And the half reaction would look like this. So one side of my cell is undergoing oxidation. Oxidation is loss of electrons. The other one is undergoing reduction. Reduction is gain. Okay, so these two half cells then are working together to cause this flow of electrons. And in order for this reaction to keep going, we need to have a steady supply of electrolyte solution. We need to keep the salt concentrations as balanced as we can to allow for this flow or movement of electrons. So kind of my missing piece here is I need a connection. I need a bridge between the solutions. And this could be as simple as like a salt water drenched rag, but this is just called a salt bridge. Salt, of course, referring to ionic compounds. So the salt bridge could be anything. Let's just say in this case it's potassium chloride. It could be sodium chloride, it could be potassium nitrate, it could be anything that is a salt that is very soluble. So it's good to use those alkali metals because they're pretty much all soluble all the time. So as these reactions are occurring, then in order to keep the charges balanced so that we can keep the flow of ions going, then these solutions are going to pull from the salt bridge what they need to balance out kind of the charges that they're experiencing. So as I'm losing electrons, the solution gets more positive. This guy is going to have to start pulling some negatively charged ions, some anions, out of the salt bridge into solution. So we're going to have to start pulling out those chloride ions into solution in order to help balance things out. We're losing electrons. We need more negative charge. That's going to come from the salt bridge. Now, kind of the opposite is true on the other side. As these copper ions gain these electrons, and we end up with copper metal on the electrode, then we have fewer positively charged ions in solution. We need to balance out those charges by pulling that positively charged cation from the salt bridge. So this is all occurring kind of simultaneously. And I have this set up as if we were in a lab, and I'm on a lab bench and I have a couple beakers, and we've set up these different half cells, and then we can play around with different types of metal. We can play around with different oxidation and reduction processes. But this is kind of fundamentally what's happening kind of in our overall setup. So a couple vocab terms, and just to make sure that we have some clarity on kind of what does what. The zinc electrode that's undergoing oxidation we call the anode. So if you've heard of an anode of a battery, that's what we're talking about here, is one of the electrodes. So the anode, for our purposes, is negatively charged, and it's the one that undergoes oxidation. The electrode that's undergoing reduction we call the positive electrode, and it's called the cathode. So again, by convention, cathode is the positively charged one. I've had students remember this before because the positive in the T, so it looks like a plus sign there. So cathode is the positively charged one. Anode is the negatively charged one. I remember the anode because of anions, right? Anions are negatively charged, so the anode is also negatively charged. So again, this is just by convention. We're not saying that they really have these charges per se, but if you were thinking about the leads on a battery or leads on a voltmeter, and one side has to be positive, one side has to be negative, and this is just the convention that we use. The one undergoing oxidation is the negative. The one undergoing reduction is the positive. Now the salt bridge, again, is the purpose of it is to allow for the flow of ions, and we're just trying to make sure that we're replenishing those electrolyte solutions in order to allow this to occur. And well, what is the point of all of this then? I have this really great system, but what would I do with it? Well, I could do with it whatever I do a battery, or whatever I use a battery for. So if I was to, with this wire, with this flow of electrons, stick something in here, like maybe a light bulb. That's pretty good. Right? So if I put a light bulb in there, then as soon as these electrons start moving through, then it's going to light up my light bulb. So the goal of this is to cause this flow of electrons. A flow of electrons is electric current, and then that electric current can be used to power something. When it's not hooked up to something, then it's just kind of ready to do that. It's potential, and so this potential flow of electrons can be used for something, and we'll get into that. We'll get into things called potential difference and such in future videos. Now, in terms of notation and symbols, it's not like I would draw this every time, although this is quite good in terms of my art. But if I wanted to represent this symbolically a little more succinctly, then I would use kind of the Voltaic cell notation, which looks like this, where I have kind of the zinc solid to the zinc in solution. And then I divide it with a double line here, which indicates my salt bridge. And then in the solution, I have copper ions, and then I have copper electrode. So the notation for these Voltaic cells is that this side is my anode. So it's always written anode, then cathode, negative, then the positive, and then I divide them with this double line that indicates my salt bridge. So this notation then is kind of a quick form that when you see this, you visualize this. This is what's happening in the cell, but these are the metals, these are the ions that are in solution, and so long as we have this setup, then we are going to be able to create the movement of electrons that's allowed in order to power things like our light bulbs or our boom boxes or whatever the kids are using these days. All right, so that's a little introduction to voltaic cells. We'll get into more about potential differences in electric currents and plating metals and all that good stuff in future videos. And if you have any questions on this, don't hesitate to ask, and I'll talk to you again soon.